In our last video, we calculated the pressure gradient, dP by dr, how rapidly the pressure needs to decrease as your distance from the center of a star goes up, so that it balances gravity, and we came up with this equation here. In the current video, we're going to now use this to work out what the central pressure in a white dwarf is compared to the central pressure in the Sun. So if we have d pressure by dr equals, I'm going to use a minus so that as r increases, pressure goes down. You could define it either way, but okay, so we've got d pressure by dr. What we now need to do is work out what the central pressure is. So if we know the differential and we want the actual value, we're going to have to integrate. It's a definite integral, but we'll fix it by knowing that the pressure at the surface of the star is 0. So the pressure in the center is going to be the integral from the surface, I'll call that a big R, the radius of the star, down to the center of minus 4/3 pi g rho squared. Those are all constants, so they can go outside the integral r dr. So it's basically the integral of r, which is a half r squared. So this comes out as minus 4/3 pi g rho squared r squared over 2 from r to 0, which just comes out as 2/3 pi g rho squared r squared. So this is our equation for the pressure in the center of a star if that star has uniform density all the way through. Not very realistic, but it'll give us a good enough estimate for our current purposes. But now, how do we compare this in the Sun to a white dwarf? Well, what we can see is that the pressure in the center is proportional to the density squared times the radius squared. Now, naively, you'd think that because the Sun had a bigger radius than the white dwarf, that means the pressure would be bigger. But also the Sun has a much lower density. If we assume that a white dwarf and a normal star have the same mass, say 1 solar mass each, then the mass is going to be proportional to the volume, which is proportional to r cubed times the density. So if we fix the mass, that means density is proportional to 1 over r cubed. So if you have two stars of the same mass, but one is 10 times smaller, its density must be 1 over 10 cubed times bigger. So what this means is the central pressure is proportional to density squared, and density is proportional to 1 over r cubed, so that's 1 over r to the 6th times r squared. So that's proportional to r to the minus 4th power. So what this means is if you have a star of fixed mass, if you make it smaller, the pressure in the middle goes up enormously, the 4th power. So what this is telling us is the pressure in the middle of a white dwarf must be absolutely vastly greater than the pressure in the middle of the Sun.